recording. Okay, so you remember last week we talked about what we talked about? We talked about A/B testing, and we talked about that example of Patriot and Colts example. Then we finished the last class with talking about central limit theorem, but we didn't talk much about it. But today we're going to continue talking about that and see how that can be useful for us. So central limit theorem tells us, basically describes scenarios in which the normal distribution arises. If you remember, most of the distribution that we were working as those real examples that we were showing the tables and we were drawing the distribution were not bell-shaped curves, basically. They were not a normal distribution. Most of the things that you're going to see outside, it is not normal distribution by itself. So, but if you remember, the empirical distribution of sample average were normal distribution. When we were taking the basically samples, then we were calculating, for example, the average of those empirical studies, we were getting a normal distribution or a bell-shaped curve. So sample average was estimating our population average. So basically the whole idea with central limit theorem is that if the sample is large and drawn at random with replacement, these two conditions are very important. We're going to see some of them just today and why those are important. So the sample should be large, and if we have a large sample drawn at random with replacement from our population, then regardless of the distribution of the population, the probability distribution of the sample average is roughly bell-shaped. That was what basically we finished last class with, and I show you one example. So today we're going to see one more example with that. So let's have this table of an unfair coin. Okay, this is an unfair coin. I just decided we have head, tails, but the chance of the head is higher than the chance of the tail. So if I take a like 1,000 sample from this, if you remember, this sample from distribution was the function that was taking the sample from this table, considering our chances. That was a special type of sampling, if you remember. We use it in that county example, like Swain versus Alabama, that we had a jury with different, basically, possibilities to be in our, basically, samples. So this is sample from distribution. I'm going to take 1,000 samples from this table, considering these chances, because it's an unfair coin. So if I take the samples, I'm going to have this table. Let's say these are heads, this is tail. So I have 631 heads, 369 tails. If I take it another one, you can see it's changing, but still it's higher. Number of the head is always higher because, of course, there's more chance here. So let's, this is basically the number we had the head. Okay. So if we do that multiple times, if you see the table, this basically is not normal distribution by itself. Okay, we have head like 60% chance for the head, tail is 40%. It's not a normal distribution by itself. But what I'm going to do here is I'm going to take these samples 10,000 times, okay, and each time I'm going to count basically the heads, okay. So if I do that, then what I'm going to end up with, okay, I take 10,000 samples, I put it in the table, the number of the heads, and then I take the histogram of those. So basically what I'm doing here is I'm taking one sample from this, like something like this, then I have this number, I take another sample, I have another number here for the number of the heads, I take another sample, another number, so I do that 10,000 times here, and I end up with this. So this is what I'm talking about with the central limit theorem, is like we end up from not a normal distribution to a normal distribution. Okay, is that clear? Any questions so far? That's what we are doing.
Is this somehow similar to what we did in some part of the project when I think it was at the end of section 2? Is it somehow similar?
I don't remember exactly like that question, but most probably, I think you had something like this in project 2, yeah. But I don't remember exactly which section it was. So that's what it is. So you see, we get a bell shape, okay? And the bell shape is basically the average is around the center, the 600. So that's basically something that we expect to see because the chance of the head was 60%. So we expect to see basically more in the around 600. Because the 600 is coming from this, not this 10,000, okay? This coming from this I'm taking basically 1,000 samples here, like same, exactly like this. I'm basically repeating this one. I'm taking 1,000 samples and I'm averaging that 1,000. I get one number. Then I do this action 10,000 times. So for that reason, you expect to see around 600 here. So you see, we end up from something not a normal distribution to a bell-shaped curve that is like a normal distribution. So let me go to the slide now. So every bell-shaped curve is called normal distribution. The average, though the average could be different for each distribution, right? But I mean, when we are talking about the normal distribution, we're talking about the shape of it. It's the bell curve shape. But the average could be different, of course. The standard deviation or a spread of the distribution could be different. But those two numbers alone determine the whole shape of our normal distribution. If you have a standard deviation of the distribution, you have the average of it, then those two numbers can define exactly how your bell, your distribution looks like, okay? And if we remember this table from Chebyshev inequality, that was telling us for all the distribution, you're like at least 75% of your distribution falls between your average plus minus 2 standard deviation. But we saw that it's much more useful when we are talking about normal distribution. So Chebyshev rules for normal distribution was different. So we were saying, if you remember, I show you all like 5 different histograms, and I show you basically the Chebyshev rule on those. And we see like, if you consider your average and you go to a standard deviation up or to a standard deviation low, you're going to have your 95% of distribution in between your average plus minus 2 standard deviation. And average plus minus 3 standard deviation was 99.73% of your distribution. So if you look at this, basically it's something like that we were calculating in confidence interval. So now what we're going to do, we're going to use these rules with the central limit theorem to do some basically study. So what I'm trying to say here, okay, the purpose of repeated sampling is to understand how a statistic could have been different. That's basically the whole idea. We were taking a lot of samples from our distribution to study the basically how a statistic could have been different for our samples. And we talk about it if the statistic is an average of a large random sample based on the central limit theorem, then we know the statistic is drawn from a bell curve. But important question remains that where is the center of the bell curve and how wide the bell curve is. The center is basically the average of the bell curves, and how wide the bell curve is basically is that standard deviation that we want to talk about it. Let's go and do another example. This is the table that we saw, I don't know, in week 6 or 7. This is the United Airlines flights with their delay. So we have like around 14,000 records, different number of the flights, different destination, and the delay that those flights had. if you remember, we saw this. This is the distribution of this table. So you can see the delay goes all the way from this. Some of them even are flying slightly lower. I mean, slightly faster. These are in the minutes. Some of them are even flying slightly. These minus are those that are, the flight basically took over earlier, like 10 minutes earlier than the scheduled time. But it goes all the way from, like you see, like on time, those like, I don't know, like 20 minutes, 30 minutes, 40 minutes, all the way to a few hours. So this was the distribution for this. So you can see clearly it's not a normal distribution. And if we see it's basically the average, the mean, and the delay, the standard deviation, this is the average of it, okay? And this is the standard deviation of this particular distribution. But if we take, okay, what I'm going to do here is just taking out the delay because I don't want to type like a sample, that column, that this each time. So I take this column, only the delay. That's the one I'm going to study. So I put it in this table, delay, with all those delays. Then if I take the sample of it and I calculate the mean, you can see this is not exactly the same, but quite close to the mean of my whole distribution, my whole table. So you can consider this as a population that we have, okay? And this is the sample that I'm taking from the population, this one. The sample size is 400. So I'm having delay, I take 400 samples and I'm calculating the mean. So each time I do, I get different mean. As you can see, like each time I run, I take 400 samples, I calculate the mean, I get a different mean. Sometimes goes higher than this, sometimes goes lower than that. You're getting high, 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 higher, lower. So what I'm going to do again, the same thing that I did with that unfair coin, I'm going to take this, I'm going to do this action 10,000 times, okay, here. So I'm going to take 400 samples from a population. I'm going to calculate the average of it, and I'm going to do that 10,000 times. So I'm going to have 10,000 different means. Each one considered up for 400 samples. So I have like this 10,000 numbers here. So I have this, like, for example, this one, this particular one, I get 400 samples. I calculate the mean. This one, another 400 samples. You calculate the mean. Another 400 samples. You calculate the mean, and you get this time. So let me hide this. So if I histogram this, what I'm going to see? If I histogram this number now, what type of distribution I'm going to see?
A normal.
Exactly, I'm going to see a normal distribution. Because this is exactly that central limit theorem that we are talking about. If you're taking a large sample and you're doing that many times, and then you're taking the average of those samples. So then if you histogram this, all these numbers, you're going to get basically a normal distribution. And remember, we end up from this distribution, okay? This is the original, basically our population distribution. And this is the one that we got from the average of all those samples. So just don't confuse this. These two are totally different, okay? Here I have one sample, for example, in this point, I have one flight that has, or I don't know, for example, 10 flight that has 100 minutes delay. But here I have, like, for example, two samples, two different samples that they have this number delay, for example, 12 minutes delay. The average of those samples, if I get 400 samples, I get average of all those delays, I get like 12. One of them like here. So most of them are falling around, let's say 17 minutes. Is that clear what we're doing so far? Any questions?
Uh, I have a question regarding the one Chosa made a little while ago. Regarding section 2 of the project, we were asked to calculate the differences within the model rate, and we ended up more or less with a normal distribution centered around 0, because we could get negative or positive numbers depending on which was bigger, the increases or the decreases. The thing is that in the last question of that section, we are asked to only take the positive side of the distribution. So if it's more or less half of a normal distribution, is it still a normal distribution?
If it's a half of normal distribution. So basically, if you eliminate totally half of the normal distribution, so you're going to end up with something like this. So it can be a normal. I mean, I don't exactly remember really what the question is in that project, but this is, it can be a normal distribution. I mean, if
Okay.
that's the question. I mean, no, it can be. If you just study half of it, no, it won't
Yes.
be a normal distribution.
Okay.
You cannot basically apply, basically you're eliminating totally this side of the distribution. You're totally throwing those data in like garbage, then you cannot apply basically the rules or the rules that applies to normal distribution on that. That's what I can say.
Okay.
Okay, so we end up from this, we got a normal distribution. So there is this question for you here. What would happen if I change this 10,000 to like 10? That's one question. And another question, what would happen if I change this 400 to 10? You remember this 10,000 is the number of the time that I'm taking samples. This 400 is my sample size. So I'm taking sample of 400.
It would look less like a normal distribution.
Which one? Which one if I change?
The simple mean graph would look less like a normal distribution, because if you change either one, the variance of the data you take for calculating the average would change.
True, if I change this, basically, if I take these 400 samples and I do that 10 times, let's see what happens. And then I histogram that, I'm going to end up with this. So each one, I mean, it's exactly clearly showing what's happening there. I'm taking I'm taking 400 samples here in this particular one. I take the average of it, average of all the delays, and I end up with 15 minutes. Then here I take another sample, I take the average of all the delays, I end up with like a 19.5 minutes of the delay. So this is, that's why it's important. I mean, you do that several times, a big number, to end up with something like this. But talking about this one is a little bit more interesting. I'm going to show you this one, the size of the samples. So if I let me do it first here. So what I'm doing here now, I'm going to my population. I take the sample of 10. And basically, I look at 10 flights. I take the average. Then that's would be the distribution. Okay. So let's now talk about this, what's happening here. So, okay, I'm going to do the same thing, but I'm going to put all those basically lines in a functions, exactly the same thing that I'm doing here. I just put it in a function. I call it sample mean. So I want to call these functions with different number of size. So this is the 400, I change it to 10 here. In this one, in this example, I changed that 400 to 10. Let me run it with 400. I want to have the shape here. That was a 400. So I want to do the same thing, but with different sizes. I want to run it with 400. So I'm going to call my function with the number 400 is my sample size. Then with 900, with 2500, and see how it's going to affect the shape of basically our distribution. It's going to take a little bit time. Is it clear what I'm doing here? Any questions? So yeah, I'm doing exactly the same thing, but with different numbers. That's why I needed this function. So I'm taking here sample of 400. I'm taking sample of 900 here, and I'm taking sample of 2,500. So I end up with this. I'm doing that 10,000 times, you remember? So these are all the average for the sample of 400, 900, 200, 2,500. And if I take the histogram, we end up with something like this. So just looking at this, what can you say? The dark blue one is for 400, the yellow one is for 900, the sample of 900, and this light blue is 2,500. Can you see any relationship between the sample, the number of the samples that you take, and the shape of your distribution?
The more samples, the less variability.
Pardon? I didn't get it, David.
The more samples we do, the less variability we have in the results.
Yeah, exactly. I mean, you see the 400 has a higher variability, the 900 has lower, 2,500 has even lower, or basically you can call it lower standard deviation. Anyway, it has, as you can see, all of them are centered around this 16 minutes, like 17 minutes, around 16 minutes. The average doesn't, the basic average doesn't change, right? The average is almost the same for all these three distribution. It's visible. You can see averages fall for here, for all the three. But what is changing basically is the standard deviation or the variance of our distribution, or basically the tail of our distribution. So you may see, you can see basically, or you may conclude there is some sort of relationship between the number of the samples we take from our population with the shape of our distribution. It's all is normal distribution. All is basically not perfectly normal, but they are bell-shaped curves, normal distribution. So let's see what's happening there. So what we did, we fixed a large sample size, draw all possible random samples of that size. If we do basically fix a large sample size, we draw all possible random samples of that size. We compute the mean of each sample, then you'll end up with a lot of means in that example that we saw. So the distribution of those is the probability distribution of the sample mean, the one that we just saw. And it's roughly normal, centered at the population mean. If you remember here, this is our population mean that I calculated here. This was our population mean, 16.65, right? I'm considering my exactly all the data that I have, all the real data or all my population. Considering all my population, the mean was 16.65. So if I do this, I get the same thing. Okay, I get the 16.65 for all these three. So centered at the population mean. But what we saw that a standard deviation of those distribution is changing relative to the size of my samples. So basically, it ends up that we can have this equation. We can have this equation. So a standard deviation of my probability distribution is my population standard deviation divided by a square root of my sample size. I mean, we saw there is a relationship here. I mean, just what we saw here, there is a relationship between the size of the sample that I'm taking with the standard deviation of my distribution, right? That's what we saw. We didn't know what's exactly the relationship with it, but obviously you can see the larger that I'm going, the number, my sample, the larger sample I get, the lower standard deviation or the variance of my distribution would look like. So it ended up that there is an equation for that. So basically, a standard deviation of our probability distribution would be basically relative to the population standard deviation divided by the square root of sample size. So let's see, is that really happening or not? Okay, I define this function variability. I want to call this function with different sample size. Exactly the same thing that I'm doing here. Okay, but I put it in a functions with different sample size. So I just want to add this and basically print. I want to print a lot of information there so we can see what's happening there. So I'm going to print basically sample size, the square root of n, the number of my sample size, basically sample mean. Then I'm going to calculate that equation that I show you just to see whether it's really happening or not. So if I run that with 400 samples, which is this one, the 400, or the one that I run here, we're going to see is this the same thing that we saw earlier. So I'm taking 400 my sample size is 400. My sample size is 400. The square root of this 400 is 20. My sample mean standard deviation is 1.95. The standard deviation of this distribution. And this is a standard deviation of my original population. If you remember, this is a standard deviation of my original population. Okay. So my original population, considering all that 14,000 raw, is 39.5 almost. So the standard deviation of my population. So if I go here, what we did here, so this is the standard deviation of my population divided by the square root of my sample size, which is 20, and you end up with this number. And you can see this is pretty close to what we expect to see, right? Based on the equation that we saw. Is there any questions so far? Any confusion? So this is just to show you what's happening with that, basically that equation that I just showed you, right? The equation was this. My standard deviation of my probability distribution for my basically samples that I'm taking is relative to basically population standard deviation divided with a square root of the sample size. And we just proved that it's really happening. This is my sample size. I take the square root of it. It could be 20. This is the standard deviation of my distribution here, my sample distribution. And this is the original standard deviation of my population divided by the square root of this, and I end up with this, which is exactly my sample mean standard deviation. Is there any question so far? It's clear? This is basically was from this, okay? This was our original data. Okay, let's have this question. So assume you're sampling from the flight delay distribution. Okay, from the table that I show you from the population. So if you repeatedly compute the mean from a sample size of 1, what will be the shape of the probability histogram? So what's the question here is, I'm taking sample of 1. The size of my sample is 1. So basically, I'm going to my population. I take 1 sample from my population. Then I go again. Go from my I go to my population. I take another sample, and I calculate the mean of it. I go to my basically. If I go to my population, I take 1 sample. Then I calculate the mean. I go another sample. Mean would be exactly the same value because it's just one value. So I'm going to do that like 10,000 times. So what will be the shape of the probability histogram? And what will be its standard deviation? That's all the question, yeah. Any idea, any insight? So the question is basically here. This is, you remember here, we are here. What we did here, we calculated 400, 900, 2,500. These are my sample size. So I want to put my sample size 1. Or basically, I want to call this, you remember this value, this function? I call it with 400, I want to call it with 1. So before I run it, I want you to tell me what we're going to see, what our distribution going to look like, and what would be the standard deviation. You remember this one? So anyone has any insight?
I think it will look similar to a normal distribution, but with the variety so big.
So you're guessing it would be like a normal, basically bell-shaped curve, but it would be very wide. I mean, the distribution would be like, okay, that's one guess. Anyone else?
The distribution might depend on the original data distribution because we're only sampling once. So I don't know, it might be.
Okay, you're getting closer. So what are we going to see? This is my original distribution. This is.
I believe we're gonna see something pretty similar, if not the same.
Okay, anyone? And what would be the standard deviation?
That I haven't thought about.
Okay, anyone else? No? Ricardo, Daniel, you always have answers. I don't know if you're still there or not.
No, I don't know, teacher.
Okay, but it's, I mean, just think about it. What I'm asking you to do here is like, go to the population, take one sample, just look at one flight, okay? And calculate the average. I mean, average would be exactly the same value, right? Because it's just one number. And then draw, basically, keep it, go another to my basically population, take another random samples.
I believe the standard deviation would be the same as the original standard deviation.
Okay, so we got it. Let's do it. That's exactly correct. Actually, what we're going to see exactly the same thing. Okay, not exactly like precisely the same thing. Anyway, because I'm going and taking randoms, but the standard deviation going to be, in this case, is like exactly the same. Even you don't need it to do this if you just can consider this equation that I showed you earlier. If you consider the equation, now my sample size is 1, right? In this equation, my sample size is 1. So it's going to be basically this is going to end up 1. So my probability standard deviation going to be exactly equal with my population standard deviation. It's correct? Because here you put the 1, you get the square root of 1 is 1. Then my probability distribution, the standard deviation, it would be exactly my equal with my population standard deviation. And that's what we are seeing here. right? And why we see exactly the same distribution is because this is my original population, the United table. So basically, I'm going to here, I'm going to take one, or if I show you the table, this is the delay table. Basically, what I'm going to do here, I'm going to take one samples. I'm going to come back again. I'm going to take another random sample, come again, another random samples. And because I'm doing that 10,000 times, and all those numbers basically will be add up to the same distribution. Is that clear? Or is there any question? No? Okay, maybe I give you another example. You can see it, how it's more clear. For example, think about tossing a coin. Maybe that's easier to imagine. If I give you a coin and I ask you to toss this coin, okay, totally fair coin even, consider a fair coin. If I ask you to toss it like 10 times, there is actually a high possibility that you see, for example, in that 10 tossing coin, you see, for example, 7, 8 head, right? If you see like 5, you expect to see 5 head, 5 tail, right? But the number is small. You're just tossing it like 10 times. So what you expect to see, maybe even if you see 6 head, 7 head, even 8 head, still you won't doubt the coin. That is not a fair coin. But if I ask you to toss it now 100 times, okay, in 100 times you expect, of course, to see 50-50, around 50%, like head, 50% tail. But even if you see 40% head, I don't know, 55% head, 45% head, maybe 60% head, still you wouldn't doubt, okay? Still you consider maybe fair coin, you wouldn't doubt about it. But if you go now 1,000 times, you toss the coin 1,000 times, you would expect again 50%, around like 500-ish head, 500-ish tail. But still 450 head, 480 head, I don't know, 550 head, they are like acceptable for you, right? So you can see the number that when the number goes higher, what I just talked is like, basically I said if you go from, for example, if you have 10, you go from all the way, for example, I don't know, just saying, all the way from 2 to 8, for example, you can have head and still is fine. If you go 100, then you expect to see this basically gap become smaller. Maybe you expect to see 40, 60, it's still you consider it fine. If you go 1,000, sorry, I'm writing on this, then maybe 450 is still, 450 to 550 is still pretty good, okay? So you see the number, the higher number I'm going, okay, the standard deviation getting lower. Even if you don't consider this, you just look at the equation, then you get the same thing, okay? The higher number of basically the sample that I have, the higher I go here, the smaller this would be, right? There's a reverse relationship between these two. The higher my sample size, the smaller standard deviation, as you see in the code. As you see basically in the code. As you see here, the higher number of the sample, the smaller standard deviation. Now I'm going to send you these questions. So this is a graded question, okay? So I'm going to send you in the chat. You have the link. So you can enter this. You can see the questions in that week 12 questions. And this is the answer part. You're going to answer here. Put your answer in front of your student number. So for question 1, you come up with one number. For question 2, you put just one number. And the answer is one number here, one number here. And question 3 is 1-2 line descriptions for the answers. Okay. And I'm going to divide you into group of 3 so you can brainstorm with each other. So this, if you answer it correctly, I add 5 grade to how to say, project to grade, okay? Question 2, as I mentioned, question 2 has 2 points. Question 1, 2 points. Question 2, 2 points. Question 3, 1 point. Extra for your part project to grade. So let me. So you all have it. Have the link in the chat I just sent you. So I stop sharing. Did you stop? Okay, because I stopped recording, I explained the first one again. So that was the question. So basically, you should remember that the sample mean standard deviation. We had this. We already talk about this equation. That sample mean standard deviation is your population standard deviation that we already have, divided by the square root of a number of the samples, which is 10 or 100 here. So if you do that, basically math, you get 20 divided by 10 because the square root of 100 is 10, so you get 2k. This is a standard deviation of a sample mean. So 14k is 2 standard deviation above the population mean. And according to Chebyshev inequality, about 95%, when we are talking about basically normal distribution, about 95% are within 2 standard deviation of the population mean. Why this allows here, this rule will be basically applies here because of the central limit theorem that we already know. Because we know if we do this, if we take 100 chosen uniformly at random with the placement, we're going to end up with a normal distribution. That's why we can use basically Chebyshev inequality rule for normal distribution. Based on that, 95% are within 2 standard deviation. So 95% of your basically data are within 10k plus 2 standard deviation, which means like 14k, and all the way to the other side between 6k to 14k. That's 95%. So the question asking us what's the chance that the sample are above 14k? So that would be 2.5 in your basically right hand side of the distribution that are above 14k, and of course there are 2.5 that are below 6k. Okay, don't confuse this. I put it here, but I should correct this. That is to below 6k. Right? Is that clear? Okay.
Yes.
The question 2 is slightly different, looking at it from different side. We already having a perfect bell shape, okay, with the mean of 100, the standard deviation of 20. So we're going to take 100 samples from this basically perfect bell shaped normal distribution. We're going to do that 100 times with replacement. And the question is, what's the chance that all these hundreds are below 50? So 50 is 2 standard, basically 2 population standard deviation above the population mean. So here, the mean is 10, the standard deviation is 20. So here, I mean, the difference between the first one, here we have this, then we take this 100 as a samples. Here, we already have basically a standard, basically normal distribution, perfect normal distribution with this. So if you consider this with that rule, 50 is 2 standard, 2 population standard deviation above the population mean. So if the mean is 10, the standard deviation is 20. So 50 would be 2 standard deviation away from the 50. So the chance of drawing one value below 50 is 97.5%, because 97.5% of your values are below 50. So that's for one example, that's just for one draw. But if you want to do for 100 times and you want to make sure all these hundreds are below 50, then it would be basically this 0.975 to the power of 100. That's basically that, how to say, this is the equation that you were talking in the second class or third class. That's what is the chance of, for example, taking all heads in 100 draw. Okay, tossing the coin, tossing one coin like 100 times, and you wanna calculate what is the chance of, for example, all heads or all tails. So this is the one. So this becomes quite a small number or big number. Any idea?
It is small.
It's small.
Yeah, it's quite a small number. So there is not a high chance of you take odd. About question 3, you want to estimate the height of the tallest person on a campus. You sample 100 people at random and compute this confidence interval using the bootstrap. And you put the upper bound as 190 centimeters, basically the upper bound of the height of a student. And one person with like around 198 centimeters walk by and you say, what just happened? You know, what went wrong here? So basically the question is here is the parameters that are highly influenced by a few values are difficult to estimate using bootstrap resampling. That's what we considered, what we talked like 2-3 weeks ago, that don't use bootstrap for high or very low percentile. That doesn't apply. If you remember when we were talking how to properly use bootstrap, for basically high or very low percentile, it doesn't apply. So you cannot use that for this example. And another point is the 100% sample is not basically similar enough to the population to estimate confidence interval of this preciseness. Sampling 100 people never gives you this precise confidence interval. Like 99.999%, you don't get this with 100%. As some of you clearly highlighted here, the sample is very small. Only 100 students is a very small population. Most of you that you put are putting the same correct answers. So that's it from these questions. So any doubt about any of these 3 questions? No? All clear? Okay, let's stop. Yes?
I still have doubts in the second one.
Second one, okay. Where is this? Where did I go? Second question. Okay, what's the problem here? Everything?
I understand about why you put by the power of 100, exactly 97.5, that part.
Okay, let's see. So this is you get it, right? 50 is the two population standard deviation above the population mean. So this is your mean. Your mean is 10. If you go 1 standard deviation, you get to 30. Another standard deviation, you get to 50, because your standard deviation is 20, right? These are the gap of 20. And the other side also, you get to minus 10 and minus 30. 2 standard deviation away from your mean. This is your mean. So according, now this is basically, this is the 95% of your data. 95% of your data falls in this part, right? because this is the normal, this is perfect bell shape, and we talk about bell shape based on that Chebyshev inequality rule. If you have bell shape, true standard deviation away from your mean are having basically 95% of your data. So where are the rest of the 5%? Can I change the color here? Basically, the rest of the 5% are here. Is here now there are 2.5%, right? And another 2.5% is here, right? Because it's a perfect bell shape, right? So we are talking about a bell shape, right? Like this. This is the basically, let's say this is your distribution. You're saying this is my 95% of the data, and this is 2.5 here, 2.5 here, and this is 95% of the data. So now the question asking you, what the chance that all are below 50? So if you take one sample from here, what is the chance it will be below 50?
Okay, so 97.5.
Yes, so 97.5%, because this is all the thing that you have. The chance of taking one sample below 50 would be all this 97.5. So now you want to do that 100 times, right? So you're taking 100 times, so it would be this to the power of basically 100. That's what we. Is it clear better now?
Yes, thank you.
So that's why we are talking here. This is 97.5. In order to do that 100 times, you have to do the power of 100. Any more questions about this? If no, I stop the class at this point. But what I want you to do is to go to the shared drive, and now we have a lab 7. Lab 7 is about Bootstrap. Okay. So you do the, I noticed there are 4 students that already did this because I put it last week, but I said then I removed it. I said don't do it, but apparently some students they just had it and they did it. But it's fine if you're not among those. Please do it now. I'm going to divide you again to the group of 3-4 students. Okay. So you can basically work together, talk about it, talk about the solutions. This is already available in that Google Drive that I sent you the link earlier. If you don't have, I share it with you again, and it's already available in the server as well. So if you are doing it locally, it's fine. Just get it from here. If you're doing it on the server, it's already there. So, is there any questions about what I'm asking? So I'm going to basically do the breakout room again, break you in the groups of 3-4. So you can finish, I guess you can finish it just like in 1.5 hours. Okay, but anyway, I'm just breaking out. So till maybe another 15 minutes, you can work together. Okay. Just show me a sign that you're getting it, what I'm asking. It's
Yes.
clear? Okay.
Thanks.
So if you needed to take break, just take break. When you are in your breakout room, then come back and talk with, the idea is you do it together, okay? Of course, I could just finish the class and say, okay, you just do it. But I put you in the group so you can talk with each other if there is a problem, like exactly the way that you do in the class. You talk with the person next to you, sitting next to you, about the problem you have. So, but I'm online. If you had questions, just ask me to join your breakout room to talk about the problem. Okay. Okay, let's do it. So let me stop sharing. Stop.